Good afternoon to all of you. Myself Deepak Upadhyay from Impulse Technology, Gurgaon, Delhi. So first, I would like to say thank you to all of you for accepting and registering yourself on this webinar on quantum technology spin-qubit devices in semiconductor by using this QTCAD software. So basically, this QTCAD is a quantum technology computer-aided design software that is developed by Canadian company Nano Academy Technology. So in this session, I will give you some presentation about this Nano Academy technology and what are the product and how these QTCAD tools are useful for quantum technology simulation, including spin qubit in semiconductor. And after this presentation, I will demonstrate you live in this software. So let's get start this session. So if we talk about this impulse technology, like what we are and what we are doing here. So basically, this Impulse technology is a distributor for this Nano Academy technology simulation software. And this Nano Academy technology is a Canadian-based company who provides the quantum technology and the nanoscale material and device simulation software. And if you want to work on up to electronics domain, like some perovskite, tandem, organic solar cell, thin film, OLED, then we have another partner, Fluxim, that work on up to electronics domain. And suppose you have some problem in your SVG server that is not good for the DFT calculation, then we can also provide you the cloud-based material simulation software Exabyte, where you can run your simulation on the online cloud resources like Amazon server, Google server, and you can download your result from this online cloud resources. So these are three major partners that we are presenting in India. So today we have scheduled this webinar on this Nano Academy technology and its product. So I will focus on this Nano Academy technology. So if we talk about this company overview, so this company was founded in 2008 by Professor Hongo, Dr. Zhu, and Dr. Lee from McGill University. So it was developed for a molecular quantum transport software that has been used around more than 10 plus years. And now they have enhanced their feature for material development through advanced digitalization and modeling tools. Now they have also emerged this address the emerging sector of quantum computing revolution, that is QTCAD. So this webinar is focused on this QTCAD software. So we have several unique features and more development are released day by day. So basically they are located in Montreal, Quebec, Canada, originally from McGill University. So this is the company overview. So if we talk about this Nano Academy technology and why this software are world-class software, so they have a team of nanoelectronics, physics, applied computing physicists, and expert developing atomistic and quantum simulation tools for advanced applications. So we have several unique features and more develop. Yes, we have several unique features: atomistic and quantum transport simulator. We can also predict the material properties, and as you know, the physical and electronics property of material, that is very important for the research and development, so that you can accelerate your time to market. And we have also fast converging advanced algorithms, and we have powerful features including machine learning in our tools, and efficient parallelism and scalable design in our course. So plenty of tutorials are there so that the user will get started quickly. And for the open source Python API, we have integration of the convenient and easy tools. And we also support a free trial license for the 1 month so that user can evaluate our software for their useful or not. And we can also provide you the 1 year update, including the new version of the patch fixes. So basically, this Nano Academy technology developed this nanodical software for the atomistic quantum transport simulator that is based on DFT and NEGF method. They have also developed this rescue software that is dedicated for the material simulation based on the DFT and DFPT in density function perturbation theory. And now they have also emerged this quantum technology simulator. So today I will focus on this QTCAD software. So this QTCAD is a about modeling spin qubit and semiconductors that is based on finite element methods. So we can predict the performance of quantum devices before their manufacturing process during design phases, leading to significant saving times, money, and resources. So if we talk about their features, so we have an electrostatic tools that can solve the confined potential of the quantum dot in semiconductor nanostructure, so that you can find the corresponding envelope function for the electrons and holes. So we also have an exact diagonalization tools for rigorous treatment of few electron systems. And also we have master equation solver, so that you can calculate the quantum transport calculation in sequential tunneling regime, so that you can enable the treatment of Coulomb blockade and predicting the charge stability diagram. And also we have a Bailey splitting calculation tools for the Bailey coupling in nanostructures. And our electric dipole spin resonance modules interface with the QT for the time dependent simulation of quantum control. And this QTCAD software can also work on cryogenic temperatures and in many practical design of solid state spin qubits. So arbitrary 2D, 3D device geometry that are defined using the mesh technology. And you can also import gate geometry from the layout file klayout. And we also support the user-friendly Python API interface, so that you can define your heterostructure and launch the simulation. So this is the key feature for this quantum technology. So if we talk about the technical background about this software, so here this is the typical heterostructure that can be hold spin qubits. So the basic principle of spin qubit are to confine single electrons or holes in gated quantum dot semiconductor heterostructure, such as this one is here. So this is typically a collection of materials layers that is used to create a potential well, which is created by heterostructure itself. And this can be lead to the formation of two-dimensional electron gas, and this generate the confinement along the z-axis. So this is the growth axis, and for providing the lateral confinement, this metallic gate is deposited on the top of the structure, so that you can find the single, double, and triple quantum dot or even more. So ultimately, once a single electrons and hole confined, it becomes possible to its manipulate its spin qubit, for the example microwaves, and then perform the two qubit by exchange interaction between the electrons and holes. So there are many technical advantages. So first, they are small nanometer size circuits. So this in principle to enable fit million of qubits on a single chips. Of course, there are many challenges to do this in practice, but in principle it could be done. And in addition, those devices can be operated at 1K temperatures, which seems very small, but it is actually very large as compared to this superconducting qubit. And this simplify a lot in control, electronics, and heat management. And finally, these devices are naturally continuation of the today's semiconductors. And so it's possible to leverage manufacturing capability of the semiconductor industry. So for these regions, many notable companies like Intel, IBM, Silicon Quantum Computing, even global industry, SD Microelectronics are working on this quantum technology. So this is the technical background. So first, it is useful to understand the vision behind this QTCAD, and this best can be done by making an analogy with the situation that is going on for the classical electronics field for many years. Now, this classical industry benefit from a well-established hierarchy of simulation software that go all the way from the process simulator to device simulator to the circuit simulator. So the idea is possible to simulate fabrication process and obtain a 3D representation of the structure that will. So the idea is possible to simulate fabrication process and obtain a 3D representation of the structure that will result from those fabrication process. And then this 3D representation can be input into the device simulator, such as for example Centaurus device, equivalent cadence. So many ticket software are available, but that is not possible for the qubit simulator. And though those performance of few devices are obtained, so it's possible to input them in the circuit simulator, in which compact model of transistor are used so that you can enable the solving of chips that contain million of components. So this is actually the integral part of electronics engineering workflow used for every day by day for the industry. But if you look at the quantum space, we quickly realize that there is no such well-established hierarchy of software, and similarly hierarchy would be illustrated here. So we will start from this process simulator. So we will start from this process simulator for spin qubit in semiconductor, and this would essential be the same for as the classical devices, but at the device simulator the things are already different. And this is the reason that spin qubit are operated at very low temperature, at which even converging electrostatic of devices that become a challenging for the conventional ticket software. And the other reason is that the operating principle of the devices are completely different and rely on different quantum physical phenomena, namely quantum effect. And so model this have to include it in the ticket tools are very different. So here you can see this is the some example that are meaningfully for the spin qubit in semiconductors. And the idea of a device simulator would start from this structure and calculate the example chemical potential for the quantum dot, or you can start stability diagram so that you can identify the single electrons or single holes regime in which spin qubit can be operated. Ultimately, at the end of this device simulator, we can go to this qubit simulator, and then this input will be fed into this qubit simulator, where we can perform the dynamical evolution that will outcome from this device simulator. And ultimately we could dream of these using this circuit simulator, in which the result of those master equation simulations could be input, and then we can simulate the quantum computing maybe tens of qubit. So in this talk we will focus on this device simulator, which is where this QTCAD mostly involved. So let me list some typical issues encountered by this nanoelectronics engineer while designing quantum devices. So first, it is difficult for the engineer that can confine single electrons variables, and even when this is done, it is also difficult to make a qubit from that confined electrons. And typically people have to study a large set of devices until they found the desired properties, which is costly in resources, money and times. It is also, even once we have a working qubit, it is also difficult to understand those physics behind the experimental data from the measurement performance and this device structure. So in particularly, to understand those physics, people have to study a large design of model specific to particular devices, which is costly in times. And ultimately, there is a lack of general simulation tools for the semiconductor qubits. So our value proposition is to streamline the design process with reliable all-in-one product, spin permit, spin qubit perform before their fabrication. And they have launched this QTCAD software in May 2022. So this is the typically the workflow for this quantum technology. So typically user will first select a spin qubit technology. So that could be different on the semiconductor device. And once this technology is selected, the user need to create a 3D representation of this structure. And this could be done by using a GMES. So basically GMES is a third-party open source meshing software which also has a computer-aided design capabilities and graphical user interface. So once this mesh is generated, it could be input in our QTCAD software through our flexible Python APIs. So the Python API enable to first load the mesh, but also define some material throughout the structure. Like you can define the dopant density, boundary condition, and that quantum model to be solved and ultimately launch the simulation. So when the simulation completed, the result can be visualized without standard Python API. So you can visualize your output in PyPlot, PyVista, or PyView. So this is the workflow that user need to follow during design a semiconductor device. So if we talk about this QTCAD models, so the model of the QTCAD are as follow. So I will quickly summarize those models. So as you can see here, there is a hierarchy of solvers. So first, this is the device geometry. So as I said in general, it can be generated by the GMS. But for simple and typical quantum data structure, it is possible to directly import the layout file, and that gated layout file in the GDS format. So from the K layout option, you can generate your layout file in GDS format, and you can import our device simulator through this Python APIs and define some heterostructure and design rule from the user-friendly Python API. So this can really save a lot of time compared with this more flexible but more involved GMS technology. So once the mesh is generated, so it will produce a mesh file, and those mesh file can be input our QTCAD software. So in QTCAD software, first step is to solve the electrostatic of the device. So here we define the boundary condition like ohmic boundary condition, Schottky boundary condition, Dirichlet boundary condition, von Neumann boundary condition. So different boundary condition you can define, and you can apply potential at each gate. Then we need to define the doping densities, and we can solve the nonlinear Poisson solver equation. So to finally get carrier confinement potential for the electrons and holes. So once the carrier confinement potential is obtained, it can be fed into our Schrödinger solver. So we are talking about the single body Schrödinger equation within the KP theory. So either effective mass theory for the electrons and Luttinger theory for the holes. So this enables to get the basis of envelope function and energy levels. So the output of this energy levels could be fed into our many body solver. So which assemble the many body Hamiltonian including all the Coulomb interaction at the quantum mechanical level. So that between the electrons and holes inside this quantum dot structure. Then this many body Hamiltonian can be exactly diagonalization within a truncated basis set, which enable to get many body eigenenergy and eigenfunction for the structure. So these are the very important quantities. So because they enable to calculate, like you can calculate the chemical potential for the quantum dots, and they can be fed into our subsequent solver. So this is the transport solver which enable to solve for master equations in the sequential tunneling regime. So the result of those basis sets can be fed into our subsequent solver. So this is the transport features which enable to solve the master equations in sequential tunneling regime for the quantum dot systems, and to get the transport peak and charge stability diagram including Coulomb blockade effect in the quantum dot systems. So another important feature is quantum dynamic. So here we can interface with the Q-tip so that you can calculate the quantum dynamic and simulate the Rabi oscillation in realistic structure. So ultimately this enable to calculate Rabi oscillation for the macromagnet spin orbit coupling or spin orbit electric dipole spin resonance. Then we can also define the gate fidelity. So these are the models that can be drawn during this quantum technology simulation software. So you can see that using QTCAD, it is possible to go all the way from this device layout to the meaningful qubit performance. So which is really a matter for the people who design and produce a spin qubit are characteristics spin qubit and semiconductors. So this is the simple and typical structure. So here you can see this is the top view of the gate layout, and this red rectangles show a simulation domain where we solve the various solvers, and these are the blue rectangle which represent the gate, metallic gate that is deposited on the top of the structure. And in the right side you can see this is the side view. So here we display the material stack for the heterostructure. So this is a very typical gallium arsenide, aluminum gallium arsenide heterostructure. So we have a gallium arsenide substrate layer. We also have a gallium arsenide cap layer, and in between the gallium arsenide cap and substrate, we have aluminum gallium arsenide layer. So that enable to block the electrons, like tunneling of electrons from the substrate to the cap. And you can see there is also a n-dope layer, which is used to bend the conduction band edge for the structure. And you can see there is also a two-dimensional electron gas layers, and finally a spacer region. So that is used to isolate the quantum dot that is formed in the two-dimensional electron gas from the dopant. So this is the typical example for the gallium arsenide and aluminum gallium arsenide quantum dot heterostructure. And now the goal here, we will simulate this structure. So in particular, we will produce this 3D representation of the structure and solve the various Schrödinger equation in the quantum dot region. So here you can see this quantum dot region is located in between the gate layer. And this is the material stack layer that I have already told you. This is the cap layer, gallium arsenide cap layer. This is the substrate layer. This is the barrier between this substrate and cap. This is the n-dope layer, which is used to bend the conduction band S, and this is the spacer. So this is the basic simulation of electrostatic at cryogenic temperature. So this is the cryogenic temperature. So as you saw, we can converge below 100 millikelvins, and commercial available TCAD tools like CentOS, TCAD, Silvaco, they are typically fail to converge below 100 K temperature. So this is the another advantage of our QTCAD software over this various available TCAD softwares. So this is already clearly an advantage by using this QTCAD, because of this spin qubit are operated at very low temperatures. And these are the some output file, and that is produced for the Schrödinger solver for the single electrons envelope function. Here you can see different slices are there: ground state, first excited state, second excited state, for the two-dimensional electron gas for the quantum dot regions. So during the live demonstration, I will show you how you can get the slices for those regions. Now many things that one can do. So once this basic simulation done, namely Poisson and Schrödinger's, so for the most simple things that one can think is to tune the gate voltage and look at how energies the electronic structure of the quantum dot to respond those changes. So this can be used to calculate the lever arm of the set of gates, which is crucial quantity for the control of those systems. So here you can see how the energy level depend on the plunger gate voltage, and calculating a lever arm for the simple making a linear fit. So this is the single electrons energy level diagram from the for the ground state, first excited state, lever arm for this minus 35.7 megavolts, and this is the lever arm for this minus 39.6 megavolt. So we can also solve the many body solver that account for the Coulomb interaction in the structure. So we can use this to calculate the chemical potential for the quantum dot structure. So this is the total energies. Here you can see this is the total energy with the n electrons in the ground state minus the total energy with the n minus 1 electrons in the ground state. So this is particularly important because it determines the current flow in a quantum dot structure. So here you can see this is the system where the drain, this is the drain region, and this is the source regions, and this is the chemical potential. So where the Coulomb potential will be applied, so that we will get the current flowing through this structure. And these are the graph for the quantum dot chemical potential. And here you can see this is the plunger gate voltage. Also we have the quantum dynamic features. So here you can see this is the quantum dynamic features which enable to calculate the Rabi oscillation under spin orbit coupling or micromagnet electric dipole spin resonance. So here this is the result of micromagnet electric dipole spin resonance simulator. So the idea is to have uniform background magnetic field which will zoom and split an electrons that is confined in the quantum dot regions. And then this addition you have a slanting field from the micromagnet which create the magnetic field gradient along the perpendicular axis. So on the right hand side you can see this is the output simulation of those Rabi oscillation in this structure. So also you can perform the quantum dynamic features in our QTCAD software. And there are of course many features, many unique features of this QTCAD software. So as I mentioned before, so it is possible to calculate the charge stability diagram by using our quantum transport solvers and by using master equation solvers that combine with the many body solver, so that you can calculate the current flowing through the quantum dot regions. And we also have a valley coupling tools for the valley splitting in the nanostructure. And finally it is possible to account for the classical electric noise in the devices and see their effect in the Rabi oscillation. So we have many more features that will come. So this is the my contact details. So for any future requirement, any technical support, you can drop the mail, you can directly contact through this given number, so that we are ready to help you. Thank you for listening this presentation. Now I would like to switch on the demonstration part. And after this demonstration, I will give you the some time so that you can ask your queries. So at the end of this talk, I will give you some time, so that time you can ask your queries. So here you can see this is the QTCAD software. So this is the QTCAD folder. And in the QTCAD folder, you can see multiple folders are there. Like here you can see this is the device simulator. So that enable to solve various classical and quantum mechanicals models over arbitrary 1D, 2D and 3D geometric. And we also have a transport simulator, so that enable to find the current flowing through the junction between the lead and the quantum system that is defined by this device simulator. Also we have a qubit simulator, so that enable to solve dynamical evolution of the quantum system that is defined by the outcome of this device simulator. So our script has been loaded in this example folder. So I can open this example folder and this practical application. So in practical application folder, you can see multiple script I have written. So this is script I have already written, and this is the layout file where the layout in GDS format will be loaded, and this is the mesh file where your GMesh file from the GMesh software will be loaded, and this is the output directory where the output from this simulation will be loaded. So first I can open this device gen. So this is the device gen I would like to open. So in this first part of this section, we will define this GMesh device gen, so that we can create the mesh for our entire devices. So including the gate structure, heterostructure stacks, based on the photomask layout for the gate structure and the quantum dot structure. And in the second part, we solve the nonlinear Poisson solver throughout the entire devices so that we can obtain the quantum dot that will confine potential and solve the Schrödinger equation in the dot regions so that we can find the eigenenergies, eigenfunctions within the quantum dot structure. So this is the device gen I would like to open. Here you can see this device gen has been opened. So basically this device gen is an open source code that was developed by this Nano Academy technology so that generate a device and it makes from the photomask layout in GDS format. So the aim of this the main aim of this device gen is to demonstrate how we can accelerate the generation of the mesh appropriation for the modeling semiconductor nano device. So here you can see this is the structure. So this is the structure that we have written this command. For this structure we have written this command. So once you run this simulation, here you can see this is the run option and it has loaded this Gmesh. So this is the same structure that I have shown you during the presentation. Here you can see this is the presentation. So this is the top view. Here you can see this is the top view for this structure. So first we can define some gate quantum dot using this device by importing two solvers. Like here you can see this is the import device generator that is used to design the mesh and we have defined their path. So once this solver you can load, then it will load your Gmesh. This Gmesh will be loaded and then we need to define the heterostructure stack. Here you can see this is the heterostructure stacks and this is the characteristics length and this is the quantum dot regions. So this is the length for this quantum dot regions. We can also define the thickness of the each material layer. Here you can see this is the cap thickness. So if I open this presentation mode, here you can see this is the cap thickness that I have defined and this is the barrier thickness, this is the dopant densities, this is the spacer region, this is the 2-deck electron gas regions and this is the substrate regions. So we have defined the thickness for each materials and we also define the number of mesh point along the growth axis. So growth axis in the sense that is the z axis. So in the presentation mode you can see this is the growth axis and then we can initialize this device generator and we can write this script. Here you can see the gated qt.txt file has been loaded and this is the mesh file. So once you load this file, then this mesh file will be loaded. And for the visualization, you can see this is the command for this visualization. So once you write this script, then this mesh will be loaded. And when you cancel this one, here you can see the dot region coordinated in microns. So in this region, we have defined the quantum dot region. Here you can see this is the quantum dot region that has been located in between the gate regions. So these are the gate and this is the quantum dot region. So here you can see we have defined their minimum and maximum value in the x and y axis. And for displaying this, we have written this command. Also, we can releveling this surface. Here you can see we can define their surface for the top gate 1, top gate 2, top gate 3, bottom gate 1, bottom gate 2, bottom gate 3. So once I cancel this structure, then it will generate a surface structure for this mesh. Here you can see this is the mesh for this surface generator. So if you show this surface, so you can go to this tool option, select this option and then select this geometry option. Here you can see this point, curve and surface has been selected. So we can select this surface labels, and in the description we can select the physical names. Here you can see this is the top gate 1, top gate 2, top gate 3, and this is the bottom gate 1, bottom gate 2, bottom gate 3, and this is the surface. So this is the surface region, and this is the top gate 1 gate regions. These are the quantum dot region. We can also define the heterostructure stacks. Here you can see this is the cap thickness, cap layer, and we can also define the barrier thickness, doping thickness. We can also define the spacer thickness, and we can also define their two deck electron gas regions, and this is the substrate regions. So once I cancel this one, it will generate a heterostructure for this mesh technology. And if you show their meshing point, so you can select this mesh option and then select this 2D. Here you can see this mesh point has been created. So the mesh point has been created in this structure. Here you can see this is the quantum dot regions. This is our gate. This is our top gate, and this is our bottom gate. Here you can see this is the thickness that has been defined. So when I cancel this one, it will define their thickness value. Here you can see if you show their thickness. So first I can select this tool option, select this option, go to this general option, select general, and then select this geometry option. So you can see this is the gallium arsenide substrate layer. This is our gallium arsenide cap regions. This is our dopant. This is our n dope layer. This is our spacer, and this is our 2-dimensional electron gas regions. And this is the aluminum gallium arsenide layers. So this is the structure that I have created. And at the end of this script, here you can see we can define the back gate. So we have defined the ohmic boundary condition for the back gate. Here you can see this is the setting for the back gate, and we can save the mesh in this gated.mss2 option. So in this mesh, you can see this file has been loaded. So once you run this script, then it will generate a mesh file. And in the second part, I can load this to Poisson's Schrödinger equation so that we can solve the boundary state in the quantum dot regions. So this is the Poisson solver, Poisson and Schrödinger solver. So in this script, you can see we have started by importing some relevant module. So this is the CT, that is for the constant, universal physical constant. And this is the mesh. So this is the mesh class, which store the information of position of mesh point, their connecting, like definition of the input file. And this is the input and output function to save and load the certain variables. And here you can see this is the material class, which store the information of the materials, so that you can define their doping densities, permittivity, effective mass, tensor. You can define through this material command. And this is the device. So this is the definition of device class, which is central to the all the simulation that is done with this QTCAD software. And a device object store the value of physical parameters and variables at each element of the mesh point. And this is the solver, Here you can see this is the Poisson solver. So nonlinear Poisson solver, which is used to calculate the electric potential and band edge profile of the device. And this is the Schrödinger solver that contain these, so that you can calculate the envelope function and eigenenergy of the single conduction electrons that will confine in the quantum dot regions. And we can load the maze, we can define this material composition, and we can apply the external gate voltage. Here you can see this is the input file. So this is the maze file that will load here. So from this command you can load your maze file, and then we can write this command to create a device. Here you can see this is the device, and we have set the temperature 0.1 Kelvin. So here you can see this is the temperature 0.1 Kelvin. And also we have defined the doping densities, and here you can see we have set up the material in the heterostructure stacks. This is the cap region where gallium arsenide is there. This is the barrier where the aluminum gallium arsenide is there. This is the dopant layer where the aluminum gallium arsenide and their doping value is there. Here you can see this is the spacer layer where the aluminum gallium arsenide layer is there. And this is also the spacer dot region where the aluminum gallium arsenide material is there. And this is the 2-deck. This is the 2-deck electron gas for the gallium arsenide, and this is the 2-deck quantum dot for the gallium arsenide. And this is the substrate layer that is created from this gallium arsenide, and this is the substrate dot regions that is created from this gallium arsenide materials. And here you can see we have applied the different potential. Here you can see this is the top gate 1, top gate 2, top gate 3, and this is the bottom gate 1, bottom gate 2, and bottom gate 3, and their voltage value. We can also define this work function. So here you can see this is the metallic gate work function that has been included, and we can define this boundary condition for each layer. Here you can see for each gate layer we have defined the boundary condition. So Schottky boundary condition has been defined, and for the back gate we have defined the ohmic boundary condition. And we have also created the nonlinear Poisson solvers, and that will solve this. Here you can see these are the some parameter that has been included, and this command is for the quantum dot regions. So once I run this script, here you can see this is the run option. Then it will first load the Gmaze. Here you can see it has starting loading the maze file that has been located in the practical application maze file, and this is our maze folder gated.maze. So once this simulation will finished, it will generate, here you can see, so it will generate a conduction band S in the V2 format. So here you can see this is the output conduction band S in the V2 format, and also it will generate a eigenenergy. Here you can see energy function also it will generate for the ground state, first excited state and second excited state. So it will generate two folder, one is for the conduction band and second is for the eigenenergy. So eigen function and conduction band will be generated. So you can wait until the simulation finished. So once this simulation finished, it will generate their output folder. Here you can see this is the triangular element, this is the tetrahedral element, and this is the total number of nodes in this device structure. Here you can see this is the boundary, physical name, surface, top gate, bottom gate, ohmic boundary condition for the back region, back gate, and these are the layers. So here you can see it has generated our mesh. So this is our mesh. This is our aluminum gallium arsenide layer, substrate layer. This is our gallium arsenide cap regions, and this is our aluminum gallium arsenide layers. So when I cancel this one, it will generate a quantum dot. So here you can see this is the quantum dot regions that is located in between the gate regions. So this quantum dot is located in the gate region. Here you can see, and this is our quantum dot structure. So here you can see our Poisson nonlinear Poisson solver equation is solving, and here you can see this is the iterations. So maximum 14 iteration it has taken. Here you can see, and it has generated their values. So you can see this is the conduction band S. It has been located in this folder, and this is the eigenfunction. Here you can see this is the energy level value in the electron volt. So for opening this conduction band S, so you can visualize in the Python API. So here you can see this is the para view. So I can open my folder. So this is the QTCAD examples. This is the practical application, and here you can see this is the output folder. So in this output folder, here you can see the output has been generated. This is the conduction band S in the V2 format, and this is the eigenfunction in the V2 format. So I can first load this conduction band S, click on OK. So this is the conduction band S, and this is the color scheme throughout this 3D representation. So this red region is for the gate. This is the top gate, and this is the bottom gate, and this in the center you can see this is the potential well. So this blue one is potential well, and if you show their color scheme, you can see the potential well is very negative, and this red region is also positive, and this potential well form between these gate regions. So using para view, we can also create a slices in the z axis. So here you can see this is the slice option, and in this slice option I can select this z normal, and I can create this slice in between these regions, between the gallium arsenide, aluminum gallium arsenide, and gallium arsenide regions. So I can move this one like that. So you can see our slice is located in between this aluminum gallium arsenide and gallium arsenide heterostructure. And we can also rescale this color. So here you can see this is the rescale option, and we can get the truly potential gate, and also it is slightly negative. Here you can see it is slightly negative. This is our potential gate and their value. So this is the conduction band S, and now the question is, does this potential well enable to hold bound state? So to verify this, we can open the eigenfunction .v2 file. So we can open the eigenfunction v2 file so that we can verify the bound state. So this eigenfunction has been generated by solving the single electrons by using this Schrödinger solver. And now you can see this is the box that is corresponding to the quantum dot regions, and we are not seeing any much because all the action is actually inside this box. So now we will make a slices of this quantum dot structure. So for this I can click on this slice option. So here you can see this is our bound state, and this will look like a confined state, and we can have a bound state in these regions. So this is for the ground state. Here you can see this is ground state. We can also see the second excited state. So you can see this is the second excited state, and this is the first excited state. So this is the conduction band, and this is the eigenfunction. So from this script you can see we have simulated the spin in the quantum dot regions by using this QTCAD software, and the result I will open in the paraview so that we can visualize the structure in the 3D representation. So it's possible from this QTCAD software to simulate the quantum dot spin qubit devices. So we can run multiple input file. Here you can see I have created multiple folders. So you can see this is the GAFET like gated all around field effect transistor. So in this structure we will perform the basic electrostatic calculation for the conduction electrons at equilibrium in the gated all around field effect transistor. So I can open this GAFET Python file. And also you can see a header is first written to import the relevant module for this QTCAD device simulator. So these are the relevant module that we need to enable during the simulations. These are the CT for the universal constant. These are the mesh. These are for the input and output. This is for the analysis. From this material option, we can import the material properties. We can also enable the device solver. And here you can see these are the Poisson solver. And this is the Schrödinger solver. And we need to define some input parameters. Here you can see the gate to source voltage has been defined 0.5 voltage, and also we have defined the metal work function. You can see this is the metal work function, and we have defined the total length of the device structure. You can see we have also defined the radius for this device structure, and we have included the mesh file, mesh input and output file. You can see these are the GAFET mesh file, and it will load the output. The output will load in this GAFET.v2 file. So once you write the script, so in QTCAD, first step is to load the mesh file. So here you can see this is the load to mesh. We have defined this script so that the mesh will be loaded. So here you can see this is the run option, and this is our mesh file. Through this PyVista, it has been loaded our mesh file. So you can see this is the gate all around field effect transistor. This is our source, this is our drain, and this is our gate. And we need to create the device structure. Here you can see we have written this command so that we can create a device. And here we have defined the FD approximation, FD like Fermi direct approximation. And then we need to specify the physical regions and the boundary condition. Here you can see these are the regions. This is the channel. These are the oxide layer, and this is the semiconductor regions. So this is the channel oxide, source oxide, drain oxide, and this is for the semiconductor. This is the channel, this is the source, and this is the drain. Here you can see we also define the doping. So doping density also has been defined for the source and drain region. And then we have defined the boundary condition like ohmic boundary condition for the source and drain, and the gate boundary condition for this back gate. And we have created this nonlinear Poisson solver so that we can get the electric potential. So when I cancel this one, it will generate electric potential from this nonlinear Poisson solver. Here you can see this is the electric potential that has been simulated by using this nonlinear Poisson solver. And then we need to define the self-consistent solutions. And here you can see this is the device parameter. This is for the electrons, this is for the holes, this is the phi, this is the conduction energy value, and this is the valence energy value. So we can also define the band region. Here you can see we can also plot the band diagram from this analysis, from this script. So when I cancel this one, it will generate a band diagram. So this is the band diagram for our device structure. And at the end of this script, here you can see we can also calculate the eigenfunction from the for the ground state, first excited state, and the second excited state. So when I cancel this one, it will first generate the ground state electron densities. So here you can see this is the electron density for this ground state. This is for the first, this is for the phi, this is for the ground state, this is for the first excited state, and this is for the second excited state. And here you can see we can get the energy levels. And the same file you can also run through our Miniconda. So if I open Miniconda application, I need to go in my C drive and then open my QTCAD folder. I need to activate this environment. So for this, I can write this command. Here you can see this QTCAD has been selected, enable. And first we can write the command so that we can load the mesh file. So this mesh file we can load. So we can write gmesh Here you can see our mesh file is located in between the example folder, tutorial folder, mesh folder, and gafet.go file. Here you can see this tutorials, this is the mesh, and here you can see this is the gafet.go file. So when I run this command, here you can see we will get the device structure. This is our drain, this is our source, and this is our gate. So this is the gate all around field effect transistor. So this is the mesh file for this device structure, and then here you can write the command so that you can run this simulation. So this is script you can run. Here you can write Python. So here you can see this is the example folder, tutorial folder, and this is our Python file. First, it will load the device structure. Here we need to mention the Python. Here you can see the same script you can run from our Miniconda application file. So this is the mesh. This is our Poisson. This is the electric potential that has been simulated with our non-linear Poisson solver. This is our band diagram. This is the hole densities. This is the phi. This is the ground state. This is the first excited state, second excited state, and here we will find the energy levels. So either Miniconda, either Python API, you can easily simulate these tutorials. And for theory and background simulation, you can visit our official website, nanoacademic.com. You can see, and this is our official website. And in the bottom of the page, you will find the document and tutorials. So this is the document and tutorials. So this Nano Academy technology has developed this nanodical for the atomistic quantum transport simulator based on the DFT and the NEGF method. Also, they have developed this rescue that is dedicated for the material simulation based on the DFT and density function perturbation theory. And they have also developed this QTCAD software for the quantum technology spin-qubit in semiconductors. Here you can see this is the theories. This is the Poisson solver. So their theory and their equations are there. So whenever you get the time, so you can visit our website so that you will get more familiar with this software. And also you can see this is the tutorials. Here you can see this is the Poisson and Schrödinger simulation for the gate all around field effect transistor. Here you can see stepwise step procedure are mentioned. So this is the device simulator, and here you can see this is the transport simulator, and this is the qubit simulator.
I'm Dr. Vimala from Dayanand Sagar College of Engineering in Bangalore. You were shown like some demo for maybe finally for a gate all around structure. Can you tell like whatever we were, since I was already used with Centaurus and Atlas tools for simulating such devices, do you have any comparison how the output will differ for this qubit and normal structure simulation? How we can able to justify that this is based on quantum simulation?
So as I have shown you in the presentation, here you can see. Centaurus TCAD, either Silvaco, they are typically failed to converge below 100 K temperature. But if you use our this QTCAD software, then you can simulate at below cryogenic temperature. So 100 millikelvin temperature you can also simulate from this QTCAD software. But at that temperature, either Silvaco or the Centaurus, they can't do the simulation.
Yeah, that is depends on temperature wise. How, since we are telling like again here also electrons and holes are going to play the role for conducting current. So those charge carriers are as a qubit we are going to consider in this simulation. How that difference were available in terms of simulation? Do you have any comparison like how the outputs will be there with TCAD and with this qubit TCAD or QTCAD? Just I
Ma'am,
want to know the comparison in terms of outputs. Maybe as you are telling, like I'm able to I understand the temperature difference.
yes,
I can agree that we are not able to do this Centaurus and Silvaco for the cryogenic temperature. That's fine. Just for in
yes, ma'am. We
terms
will
of charge carriers, I need some clarifications.
Yes, ma'am. We will share you some PDF, the comparison between the Centaurus, Silvaco, and with our QTCAD software.
Okay.
So we will share this.
Yeah, yeah, sure. Thank you.
So qubit will not be possible neither in Silvaco nor in Centaurus. So quantum bit will be possible in QTCAD only. That is a unique feature of this tool. And there are so many papers. There are some papers also there, which is published on FDSOI and some other applications. So it is available on the website. Deepak, can you show some QTCAD papers, which is published by Nanoacademic Technology and ST Microelectronics?
It's available in the web page, Nano.
Yes, here you can see.
Yes, you can see here this
This
one.
is our website, and this is the technical insight. Here you can choose this QTCAD,
Hmm?
and then you will find the publication papers.
Yeah, yeah. Maybe that might give some clarifications.
These are
Thank you.
some quantum TCAD published paper.
Yeah, yeah, sure. Thank you. Thank you for the input.
So authenticity of the paper will be justified by that published paper. And since it is a quantum technology, it is very emerging technology. So there is no other player who is working on spin qubits. So Nanoacademic Technology is the only company where you can simulate the qubits by using this tool. So since ST Microelectronics is also published this tool, this paper by using QTCAD with joint collaboration between Nanoacademic Technology. That will justify that ST Microelectronics is very popular company. So they are jointly working together and doing the fabrication and publishing some papers. Centrus TCAD is basically uh, uh, like working on TCAD device simulation. That is not able to simulate on qubits.
Qubits. Okay.
Qubit is basically the emerging technology that people have got started. So that's why very little paper will be there. But in Centrus, there is no qubit paper.
Sir, in the website, they are given some trial license for 30 days. Is there any demo versions were available? Maybe now he explained the working of how we can use the QTCAD, whether you are able to share that uh, video or any other demo versions were available for the procedure, how we can able to use this QTCAD.
Yeah, that already then shown the procedure. So just create your account on the
Okay.
portal and then you have to follow the installation procedure
Hmm.
that is given on the documentation page.
Okay, we can get the some trial versions also there. I
Yeah,
think 30 days they were mentioned. We can able to use for 30 days this QTCAD.
yeah. Trial version is just to show the features only of the software.
Okay, we are not able to do any simulations there in that.
Simulation will be done, but not authorized to publish the paper.
Oh, okay. Now, not in that level. At least flexibility of using how to use the tool in that level.
Yeah, in documentation, the tutorial is everything is there, which
Okay.
need to be run, and videos need to be watched. These are tutorial that you have to read it out, and
Okay.
then you can perform it.
How much the cost of this license for QTCAD? Single user?
First is basically we have to discuss one to one. It is not yet like different policies are there,
Okay.
like 1 year, 2 year, 3 year, 5 year. Not a permanent because it is developing phase.
Okay.
There are so many development is about to come,
Yeah,
and
yeah.
recently few qubits are supported. In coming future, so many qubit will be supported. So perpetual license will not be beneficial for the participant, because after period of time, many updates will become, and the perpetual license will become absolute. So that's why time duration leverage license will be more better.
Okay. Maybe I
So
will
Nirmala ma'am, you
communicate
can
further.
also unmute your mic and ask your queries. Yeah, please. So those who are interested, they can also discuss one to one on the requirement or something to us. So you can already have our email or contact information, either technical queries or whatever the software requirement. Then please do let us know. We will definitely help you to boost your research in this particular domain. So thank you everyone. Thank you for your time which you have given today. Please keep in touch with us. Thank you very much.
So once again, thank you so much to all of you.